Welcome to the fourth part of the motion series. In this video, we are going to learn about the scalar and the vector quantities and also about the concept of mass and weight. So, without any further delay, let's soar the sky. Quantities. In the chapter of measurement previously you must have read about physical quantities. Now those physical quantities that only has a numerical value which is known as its magnitude are known as scalar quantities. So the definition of scalar quantity is the physical quantities that only has a magnitude or a numerical value are called scalar quantities. Some very good examples would be distance, speed, temperature, etc. Now let's talk about the vector quantities. What are vector quantities? Those quantities that not only possesses any particular magnitude or numerical value, but from those quantity we will also get to know in which direction they are headed to. So let's come to the definition. Those physical quantities that have both magnitude and direction are called vector quantities. Some very good examples would be displacement, velocity, weight, force, etc. Now we will talk about various scalar and vector quantities and compare them for your better understanding. Let's discuss about the first scalar quantity, which is distance. It's the most basic scalar quantity. What is distance? What do we understand by the term distance? Distance is basically the measurement of actual length covered by an object. Any object who is covering a particular length, that entire length will be considered as its distance. Say for example, a person is starting from point A and reaches at point B, which has a length of 100 meter. Again he is going from point B to point C, which again has a distance of length of 100 meter. So his total distance will be AB plus BC, which is 100 meter plus 100 meter, that's 200 meter. So this will be the distance covered by that man. What is displacement then? Right now I have told you about distance being a scalar quantity. Now displacement is the shortest distance covered by an object in a particular direction. Now two key points are there. It's the shortest distance and it has a particular direction. It is the shortest distance covered by an object in a particular direction. If you see this particular diagram, here a person starts from point A, reaches point B, which is 100 meter. Again from point B he reaches to point C, which is 100 meter. His distance would be 100 plus 100, 200. Just now I told you that. But if we are supposed to calculate its displacement, which is the shortest distance covered by him, it would be this line. So how do we find this out? For this particular thing is a right angle triangle, we can call it that. And in right angle triangle, there is a particular theorem which is known as Pythagoras' theorem, which states that the hypotenuse square is equal to the sum of the square of the perpendicular and the base. So here AC is the hypotenuse, AC square is equal to AB square plus BC square, and so AC will be root over of AB square plus BC square, which is around 141.42 if we calculate it. Okay, so this will be your shortest distance or displacement. To know and understand distance and displacement in a better way, let's see how it works practically. The boy starts walking from point A, then he goes to point B, and then from point B to point C. This shows the total distance he covered while starting from point A and ending at C. Then he again walks from A to C, but this time taking the shortest route possible diagonally. This gives us his total displacement. How do we know whether the motion of a body is slow or it's moving very fast? We have to take into two factors into mind: the distance covered by the body and the time it takes to cover that particular distance. Say for example, there is a place A and there is a place B. The distance between them is 500 meters. Let's see how much a man takes by walking to reach to this particular distance, which is 500 meters. He takes 15 minutes, and if we convert it into seconds, it is 900 seconds. Next, a car covers the same distance in 15 seconds. And next, a bus covers again the same distance in 25 seconds. So here you can see the distance is fixed. It's not changing. It's 500 meters. That's the same distance which is being traveled by the man, car and the bus. But their timings are different. So from here we can say the man is having the slowest motion. Next comes the bus, and the car here is exhibiting the fastest motion. So these two are the factors to determine whether a body is having a slow motion or it is moving very fast. So from the concept of slow and fast motion, we get the idea of the second scalar quantity, that is speed. What is speed? The distance covered by a body per unit time. The distance covered by a body per unit time is called its speed. Speed can be derived, speed of a body can be derived by this following formula, which is distance covered by the body divided by the time taken by that body to cover the distance. So here you can see the formula is S is equal to d by t. So according to that, if a body covers 100 kilometers of distance in 2 hours, we can convert it into 50 kilometers in 1 hour. So the speed of that body will be 50 kilometers per hour, and hence it is a scalar quantity. So it only has a numerical value or magnitude. Now let's talk about its vector counterpart, which is velocity. Velocity of a body is the displacement of the body in unit time at a particular direction. So the displacement instead of distance in speed and also at a particular direction. The velocity's formula is displacement by time taken at a direction, which is S by t. Now, my dear students, please make a note of it. The symbol of distance is small d. But when we are talking about displacement, its symbol is S. So, V is equal to S by t. And the example is again same as speed, which is 100 km per hour. But here the difference is it's showing a direction as well. That is 100 km per hour, the body is moving towards east direction. So, these are the very vital points to keep in mind. So, there is a very vital point of difference between speed and velocity. The speed of the body helps us to know about how fast the body is moving, regardless of its direction of motion. It only tells us about how fast or how slow it is moving. Whereas, the velocity of the body actually makes us understand the direction of change of the position of the body from one part to another. With the help of velocity, we not only know how fast and slow the body is moving, but we can also tell how it is changing its direction from one point to another. So my dear students, so far if you have enjoyed this video, please go ahead and hit the like button and please subscribe to our channel to get more such informative videos. Let's solve a problem based on velocity. In here, you can see a bus travels 90 kilometers towards east in 1 hour and 30 minutes. So let's find out how much its velocity will be. So displacement of the bus, that is S, is 90 kilometers. time taken by the bus is 1 hour and 30 minutes. Now, this is a very critical thing as the displacement is given in SI units, that is in kilometer, but the time partially is given in SI and partially in CGS. So we either have to convert both the units completely in CGS or we have to convert both the units directly in SI. Since rest of it are given in SI units, so we are just converting the 30 minutes part to SI. That is 1 hour, 30 minutes means and half hour. 1 hour plus half hour, which gives us 3 by 2 hours. Now we will put in the formula of V is equal to S by T, that is velocity is equal to displacement by time taken, which is 90 kilometer divided by 3.2 hours, which is 90 into 2 by 3, that gives us 30 into 2, which is 60 kilometer per hour towards east. In the beginning of the problem, it was given it was moving towards east, and since velocity is a vector quantity, you have to mention its direction. So if you want me to solve more numericals based on velocity, displacement and motion, please write in the comment section below. So from the concept of speed and velocity, we get the idea of two new things: uniform motion and non-uniform motion. What are those? When a body is covering equal distances in equal intervals of time, we call it a uniform motion. But if the body covers unequal distances in equal intervals of time, it is said to be in non-uniform motion. Say for example, when a body in every 1 hour is covering 100 kilometers, it is said to be moving in uniform motion because its speed would be 100 kilometer per hour. It's not changing its speed, it's constant. But if a body is changing its amount of distance covered in every hour, say for example in the first hour it is covering 100 kilometer, next hour it's covering 150 kilometer, and the next hour it's covering 80 or 90 kilometers. So it's the amount of distance that it is covering, it's varying in every hour. So it is traveling in non-uniform motion and its speed also changes from time to time. Uniform and non-uniform motion gives us the concept of acceleration. What is acceleration? The rate of change of velocity of an object in a particular time. Okay, so how do we calculate it? Acceleration of a body will be calculated by using this following formula, which is final velocity of a body minus the initial velocity of a body by time taken. The final velocity is indicated by the alphabet V, initial velocity by U, and time we know as T. So V minus U by T is the formula for finding out the acceleration of a body, and the unit of acceleration is meter per second square. So if the final velocity V of a body is greater than its initial velocity U, then we will have positive acceleration. If V is greater than U, then we will have positive acceleration. For example, here V is 100 meter per second of a body, U is 50 meter per second, that's initial speed of the body, initial velocity of the body, and the time taken in changing this speed or velocity is 5 seconds. So acceleration of the body will be V minus U by T, which is 100 minus 50 by 5 meter per second square, which is 50 by 5 meter per second square, and the answer comes out to be 10 meter per second square. So the acceleration of the body will be 10 meter per second square, and this is how positive acceleration look like. In the second case, if the initial velocity of the body is greater than its final velocity, that it's reducing its velocity in the course of time, then negative acceleration or retardation, which is another term for negative acceleration, occurs. Let's see this example. u, or the initial velocity of the body, is 100 meter per second here, and its final velocity is 50 meter per second here, and the time taken is 5 seconds. Now acceleration's formula is v minus u by t, so it will be 50 minus 100 by 5 meter per second square, which gives us minus 50 by 5 meter per second square, and the answer comes as minus 10 meter per second square. So this minus sign indicates that the body is slowing down, that is, it's having a negative acceleration, or we can also say that it is retarding. The third and the last scalar quantity of this chapter is mass. What is the mass of a body? The amount of matter, that is the amount of particle inside a body, that is contained inside a body, is the mass of the body. So mass is a scalar quantity. It is constant and does not change from place to place or time to time. So if a body has a mass of 1 kg, that mass of the body will be constant whether it's in any place or whether it's measured in the morning or in the afternoon, irrespective of time, irrespective of any place, the mass of a body always remains constant. So the unit, SI unit of mass is kg, that is kilogram, and the CGS unit of mass is gram. So how do we measure the mass of a body? The mass of a body is measured by a simple instrument known as the beam balance. If you can see in the beam balance, there is a horizontal metal rod which is supported by a vertical metal rod, and there are 2 pans on the either side of the horizontal rod which is fixed or suspended with the help of a metal wire and with a hook. So in this beam balance, when we are supposed to measure the mass of a body, we put the body in one of the pans, and in the other pan we use standard variations of different masses which are certified by the government, those standard masses, to measure the mass. As soon as both the pans are in the same equilibrium or balance, they are in a same straight line, we will be able to know what the mass of the body is. The complementary vector quantity for mass is weight. What is weight of a body then? The force with which the earth attracts a body towards itself, that is the weight of the body. So what are the key points? The force with which the earth attracts a body towards itself. So that is the weight of a body. First of all, it is a vector quantity, so it has a direction. Second, it is directly proportional to the acceleration due to gravity, which is g. Now, every celestial body, every planet possesses a separate gravitational pull. The gravitational pull of each and every planet is different, and that is the same case for the other celestial body as well. So g, or the acceleration due to gravity on Earth, is 9.8 meter per second square. So here g is 9.8 meter per second square. So the weight of the body will be calculated as mass of the body into this gravitational force. So unlike mass, weight is not at all a constant thing. Let me explain that to you with the help of a numerical problem. Mass of a body is constant, which is 2 kg, and the gravitational pull or acceleration due to gravity on Earth is 9.8 meter per second square, as I have already told you. Now, if we calculate the body's weight on Earth, it will be mass multiplied by the gravitational force, that is GE, on Earth, which is 2 kg into 9.8 meter per second square. That comes up to be 19.6 Newton or kg per meter square. From here we get to know the SI unit for weight is kg meter per second square or Newton. Newton is also the unit of any force. Alright, but the gravitational pull or acceleration due to gravity on the surface of the moon is 1/6 of that of Earth. That means whatever gravitational pull we experience on the planet Earth is 6 times more than that of the gravitational pull on the surface of the moon. So 1/6 of Earth's gravitational pull is 9.8 meter per second square, which gives us 1.63 meter per second square. So if we calculate the weight of this same body on the surface of the moon, it will come up to be mass into the gravitational force of the moon, which is 2 kg into 1.63 meter per second square, that is 3.26 Newton or kg meter per second square. Now you can see the weight of a body on Earth is completely different from the weight of the body on the moon. That means we can also say weight is basically the heaviness of a body based on a particular place. It varies from place to place and from time to time. And if you know that in the high altitudes near the poles, the weight of the body will be in a very little quantity, it will be a bit smaller. Why do you know? It will be lesser because the gravitational pull of the Earth towards the pole is a little bit lesser. It's not exactly 9.8 but some points less. So if we calculate the weight of a body on the equatorial area, it will be a bit more than that what is calculated in the polar region. So how do we measure weight? Weight is also measured by a very simple instrument known as the spring balance, and this is how it looks. So my dear students, thank you for watching this video, and here we come to the end of the motion series. In the next video, we are going to bring up a whole new topic altogether. So keep watching.